Let's get going with today's lecture. So the last section, we were introducing you to derivatives. The last two sections introducing you to derivatives, and you probably had to calculate a lot of derivatives by hand. Yeah. So first off, let's remind you of the definition of a derivative. There's a bunch of logically equivalent definitions. One of the things I was afraid of is you might get lost in the notation that we use. So tons of notation saying the exact same thing. So let's say y is equal to some function f of x. So we're going to talk about the derivative of y, or the derivative of f of x, same thing. One way we might represent it. F prime of x, the derivative of f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Use that several times, right? Logically equivalent definition. No difference here. We can say the derivative is the limit as z approaches x of f of x minus f of z all over x minus z. You still have the denominator going to 0. As z approaches x, that goes to 0. As h approaches 0, that goes to 0. As z approaches x, the difference up here gets closer and closer to 0. As h approaches 0, the difference here gets closer and closer to 0. So you got a rise over a run, where the quotient is getting closer and closer to 0 in the numerator and denominator. Now the way to write it. Rather than writing f prime of x, we could just as easily say y prime. It means the same thing. Yeah. Now y prime is, another way we write it is dy dx. The derivative of y with respect to x. Another way we write that is, it's the limit as delta x goes to 0 of delta y over delta x. The limit of your rise over your run as the 2 points you're calculating your slope from get closer and closer together, where the distance between them gets closer and closer to 0. So this is how you get derivative functions, or we also had the notion of getting a derivative at a point. So rather than getting a derivative function, if we want to get the derivative at a point, say c, what's the derivative of f at c? What's the slope of f at c? Well, that's the limit as x approaches c of f of x minus f of c all over x minus c. Good? Yeah. And you've seen an equivalent one like this where we're using x now. Not going to write them all out. Yeah. All notation saying pretty much the same thing. Now, nobody actually calculates these derivatives by hand. And unfortunately, it's likely going to be the case that 2 years from now, when I ask you for the definition of a derivative, you're not going to have a clue. I'll be very happy if you know it 2 years from now. That would be very impressive. But you're most likely not going to, because you're going to use these rules to calculate derivatives from here on out. And you're going to stop doing it by hand. Doing it by hand, very tedious, very time consuming. These are very fast. And you'll be able to calculate derivatives pretty quickly. So here's the rules, and we're going to prove each of these rules today. Okay. But just quickly explain what they are. So if u is some function f of x and v is some function g of x, okay, all these things hold. First one, the derivative with respect to x of some constant is 0. How much does a constant function slope? 0. It doesn't. 0. Okay, next one. The derivative with respect to x of x to the n, this is what we're going to call our power rule. How do you take its derivative? You bring the n down and subtract 1 from your exponent.
And we're going to prove all these.
We're going to prove all these. But quickly, what that is saying is, what's the derivative of x to the 5? That is 5 times x to the 4.
That's super simple.
It's super simple. And so you can just calculate like that, and you don't have to go through the pains of actually proving that anymore. Although you could prove it, and that's how it would come out. Next one. The derivative of a constant times a function is equal to a constant times the derivative of the function. So you can pull a constant outside of a derivative and it doesn't change anything.
Wouldn't this c be 0 though?
No, the c can be any constant. So give you an example of what this is saying.
Oh.
This is saying if I want to know the derivative with respect to x of 2 times x to the 5, I can pull the 2 out, and so this is the same thing as 2 times the derivative with respect to x of x to the 5. And then what's the derivative of x to the 5? 5x to the 4. So this would be 2 times 5 times x to the 4, or in other words, it would be 10 times x to the 4. And here's the derivative of that.
Okay, I see.
That's all it's saying. You can pull the constant outside the derivative, then calculate your derivative.
So what if it was like 2 plus 5x5?
Right, so if it was 2 plus something,
then it would be 0.
Then it would be 0. You're not justified in saying that yet. You'll be justified after we talk about this. Oh. The derivative with respect to x, right here. The derivative with respect to x of the sum of two things is equal to the sum of the derivatives. So now you can do that. What's the derivative of 2 plus x? It's the derivative of 2 plus the derivative of x, and the derivative of 2 is 0. And what's the derivative of x
It's
with respect to x?
Whatever x is, what do you mean?
What is the derivative of x with respect to x?
Would it be
You have the information to calculate this, or you can just think about it intuitively, first of all.
1.
1, what's the slope of that function?
Wow,
1.
Oh.
But here's another way you can think about it. X is the same thing as x to the 1. Use your power rule. Bring down the 1, so you get 1 times x to the, what's 1 minus 1? 0. And x to the 0 is 1, so it's equal to 1.
oh that's
Or if I didn't write it like this, and I had instead written it in a more telling way, I could have said, what's the derivative of x with respect to x?
there's the same one.
1. This says the same thing as that, right?
Okay, that makes sense.
Okay. This one will be surprising. So the derivative of a sum is the sum of the derivatives. The derivative of a product is not the product of the derivatives.
Okay.
And you're going to memorize this rule. The derivative of a product is, the mnemonic you'll remember is the derivative of the first times the derivative of the second plus the second times the derivative of the first.
First times the derivative of the second
Plus the second times the derivative of the first. And you'll memorize that mnemonic, and you'll remember that's how you take the derivative of products. And the derivative of quotients, similar thing. You're going to remember low d high minus high d low, square the bottom, and away we go. The derivative of a quotient is equal to the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Low, meaning the bottom, d high, meaning the derivative of the top, minus high, d low, square the bottom, and away we go.
Okay.
That's the mnemonic you'll learn to remember. Low d high, minus high d low, square the bottom, away we go.
Alright.
Now, you can take the derivative of a function, and then take its derivative again, and again, and again. You can take as many derivatives as you want. So, if you're going to take 2 derivatives of the function, then we mark that as f double prime of x. This means take the derivative, then take it again.
Take the derivative of the derivative.
Right, so if I have f of x is equal to x to the 5, what's f prime of x?
Same thing.
No, what's the derivative of that?
5.
Oh,
Use a power rule.
5x.
5 times x to the what?
Power 4.
4. Now calculate its derivative again. And what do we get?
15x to the power.
How are you guys getting 15?
20.
4 times 5 is 20.
What the heck?
20 is.
Oh, because I took
Bring down the 4. 4 times 5. Oh, you were subtracting, then bringing down. Bring down, then subtract.
Okay, gotcha.
So bring down gives us 20 times x to the 3.
Yep.
And so there's the second derivative.
And
And you can calculate the third derivative, the fourth derivative, the fifth derivative, and you keep going to your heart's content.
And you can go infinite negatively too.
I don't know what you mean by infinitely negative.
I can keep taking the exponent negative forever. Because once
Let's
I
keep playing with this. You're thinking something's going to happen that's not going to happen. Instead, it's going to run to 0. Let's take the derivative again. So now let's look for f triple prime of x.
60.
Bring down the 3 and we get 60x squared. There's that. Now, if we take the derivative again of that, now we're tired of using all these tick marks. We don't want to blow up and have a ton of tick marks. And so what we end up doing is we write f parenthesis, put the number of times, and parenthesis, x like that. And so you don't think that we're taking it to the 4th power, but we're taking 4 derivatives.
Yeah.
And so that is going to be equal to, take the derivative of that, we get 120x, right?
Yep.
Now take the derivative of that, what do we get? What's the derivative of x?
1.
1. What's 1 times 120?
120.
120. Perfect. Now what's the derivative of 120? 0. The derivative of constant is 0.
Can't you go into negative exponents?
What is the
This is 120 times x to the 0. Okay, let's go to negative exponents. Let's do what you want, right?
Alright.
So bring down the 0. So we get 0 times 120 times x to the negative 1. What does that equal?
0.
0.
What about x to the negative 2?
Bring down the negative 1 now, so you get negative 1 times 0 times 120.
Where are you getting the 0 from?
Well, because it's 0. So now you're saying, what's the derivative of 0? You're saying, well, you can think about 0 as times x to the negative 1.
Oh, I mean,
So what is,
And it's going to be 0, 0, 0, 0 from there on out.
alright, that
what
makes
is the derivative of a negative function, or of x to the negative?
We'll do some of those, but you can still use your power rule.
Okay.
But good. So establishing some intuition. So our basic rules so far. Oh, so we were on notation. So the second derivative of y with respect to x, taking the derivative twice, you can represent that as f double prime, or it's d to the 2y all over dx squared. Now this isn't really doing a square to anything, it's just notation. This just means take the derivative twice of y with respect to x.
Wouldn't it be written in parentheses then?
Or in other words, it's the derivative with respect to x of dy dx. So we do the parentheses here. So I do, if I'm taking the nth derivative, so
Yeah,
n could be
so-
something like 10, then that's f to the 10 in parentheses to let us know we're taking a derivative. But here, this notation isn't ambiguous. We know exactly what it means. So it would be d10y over dx10. Just notation for taking all those derivatives. Okay, so these are the basic rules you're going to use over and over again. Now let's go through and prove each of these rules. So proving the first rule, derivative of a constant is always 0. Obviously, a constant function has a slope of 0. That's what we expect it to be. But let's prove that the derivative of a constant is always 0. So proof, if f of x is c, where c is some constant, some real number, then f prime of x is going to be 0, its derivative 0. So I'll let f of x equal c. Well then what is f prime of x? Pick whichever definition we want. I'm just going to use the one this one right here. So then f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, right? But if our function is a constant function, what do I get if I plug 1 into the function? C. What do I get if I plug 10 into the function? C. What if I plug minus 1,000 into the function? It just spits out C no matter what x you plug in there. So what is f of x plus h? It's just C. And what's f of x? It's just C. No matter what input you give it, it always spits out C. It's a constant function. So that just gives you C over C, the limit as h approaches 0 of C minus C. But what is C minus C? 0. And 0 divided by anything is 0. So we're talking about the limit as h approaches 0 of 0.
You're saying the first one trumps the bottom?
No, the first one is 0. Remember, as we're taking the limit as h approaches 0, h is some small number, not 0.
Okay, I see that.
Right? So now, 0 divided by some really, really small number, it doesn't matter, it's 0. So yes, 0 goes to 0 faster than h goes to 0. Because 0 is already at 0.
Yeah. Okay, gotcha.
Okay, so we get 0, and the limit as h approaches 0 of 0. What is the limit of a constant? It's just that constant. Good? So there's our first proof. The derivative of a constant is 0. Next one, was afraid to do this without giving you some algebra, since you guys have not been great on your factoring. So,
I've seen this before.
oh, cool.
From what?
We're going to multiply this out.
Okay.
I'm going to take a minus b and multiply. Let's do this with the smaller one first. We'll come to this down here. Let's take a minus b and multiply it by a squared minus ab minus b squared. You with me? First I'm going to multiply my a through to everything. So what's a times a squared? A cubed. Oh, those are supposed to be pluses. What's a times a plus b? Or sorry, what's a times ab?
A squared.
A squared b. What's a times b squared?
A squared.
ab squared. Okay, perfect. Now what's negative b times a squared?
Negative b a squared.
Or negative a squared b if we say the a first, right?
Yeah.
What's negative b times ab?
Negative a. What?
Negative ab squared, right? Multiplying these two together.
Okay, I see that.
And then negative b times b squared is
B cubed.
minus b cubed. And so now, add these two together. Notice all the middle terms go out and you're left with a squared minus b squared. Or a cubed minus b cubed. Thank you. You see it?
Yeah.
if we were to do this with more terms, say now that this inside went a to the 4 plus a cubed, notice that my powers of a go down and my powers of b go up.
Yeah.
So this is a to the 4 times b to the 0. You can think about it that way if you want.
Yeah.
Plus a cubed times b to the 1 plus a squared times b squared plus a times b cubed plus a to the 0, b to the 4, if you want to think about it that way.
Yeah.
Or just b to the 4. Think about what happens when we multiply this out. A times a4 gives me
A5.
a5. And then, when I get a4b here, I get negative a4b here. When I get a cubed b squared here, I get negative a cubed b squared here.
Yeah.
Yeah.
And so all my a's and b's cancel out except for a times the first term and negative b times the last term.
As long as they're in that order.
As long as it has this pattern to it. The order doesn't matter.
Right.
If I do 3 plus 1 minus 2, that's okay. So order doesn't matter, but as long as it follows this pattern, then it comes out this way. You see it?
Yep.
So in general, a to the n minus b to the n is equal to a minus b times a to the n minus 1 plus a to the n minus 2 times b, dot, 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 following this pattern. This is a special case where n is 5. So a to the 5 minus b to the 5 is equal to a minus b times, what's 5 minus 1? 4 times 5 minus 2 is 3b times 5 minus 3 is
2.
dot, 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 until we get to our last terms.
4.
So, can you read that notation okay? You see what it's saying?
Yeah, that makes sense.
Okay, so with that, we're ready to now prove our next one, our power rule. What's the derivative of x to the n? It's n times x to the n minus 1. What's the derivative of x to the 5? It's 5 times x to the 4. So we're going to prove this in all cases all in one go.
Yeah.
Okay.
So, here we go. So, if f of x is equal to x to the n, then f prime of x is equal to n times x to the n minus 1. That's what we're proving. Now, we're going to assume, we're only going to prove this when n is a natural number. It turns out it's true for any real number that you put up there.
What do you mean by natural number?
0, 1, 2, 3, 4, 5,
Okay.
etc. Not negative. We're not proving it for the negative case. And not x to the pi.
Okay.
But you could plug in pi and the rule still works. It's just proving it for all real numbers is more complex.
Okay.
So we won't be doing that in this class. So I'm just going to prove it for the case of natural numbers. So let f equal x to the n for some n in the naturals. So n something like 7, 13, 191. Okay, so then what's the derivative of f with respect to x? What's the derivative of our function? It's equal to, this time I'm going to use our second definition.
Okay.
It's equal to the limit as z approaches x of f of x minus f of z over x minus z, right?
Mm-hmm.
Now what is f of x?
It is x.
X to the n. What's f of z?
X to the n.
Z to the n.
Or z, yeah.
If I plug in z for x, I get z to the n, right?
Yeah.
All over x minus z still, right? Now my problem is that this denominator is going to 0. I need to somehow cancel out that denominator. And I'm going to use this rule to do it. X to the n minus z to the n can be rewritten as x minus z times x to the n minus 1 plus x to the n minus 2 times z plus x to the n minus 3 times z squared plus dot 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 plus x times z to the n minus 2 plus z to the n minus 1.
How do you know how far you're going into that infinity?
That's the point of the triple dots.
Yeah.
We're saying for any natural number n.
Oh.
N could be 10,000. In that case, you write out all 10,000.
Okay, gotcha.
So that's the point of that notation, is that you don't have to keep track of them all. But how many terms are there going to be? Maybe we should have specified that. How many terms did I have in here?
4 or 3?
3. I had whatever n was here.
Yeah.
When n was 5,
Oh. Okay.
okay.
I gotcha.
Yeah.
Because you have when a is to the n minus 1, the n, and then to the 0.
Yeah.
So if you count from 0 to 9, you count 10 numbers. So if you count from 0 to n minus 1, you count n numbers.
Okay.
Okay, so rewriting this as this right here. And what was the point of doing that?
You have an x minus z common factor.
I have an x minus z and an x minus z. The whole point was I need to cancel out this x minus z somehow because it's going to 0. It's stopping us from taking the limit. And so we can cancel this out with that, and we're left with this thing, right? And now we can take our limit as z approaches x.
Oh.
And as z approaches x, then we get x to the n minus 1 times x to the n minus 1. How did I get x to the n minus 1 here? It's x to the n minus 2 times z.
What are you using?
I'm replacing all my z's with x's.
Oh, because it approaches that. Okay.
Right.
Gotcha.
So, do you see why this is still x to the n minus 1? It's x to the n minus 2 times x,
Yeah. Okay. Gotcha.
which is x to the n minus 1. When you multiply terms, what do you do to the exponents?
You combine them.
If I have a squared times a cubed, what do I have?
A
A.
to the power 5.
A to the 5 or the 6?
I.
5.
5. When you multiply terms, you add exponents. So when I replace my z with an x, what do I have here? I have x to the n minus 2 times x to the 1, if you want to think about it that way. And n minus 2 plus 1 is n minus 1.
Okay.
Similarly, for this term, here I had x to the n minus 3, but then I need a plus 2, which gives me x to the n minus 1. All the way down.
Okay.
Z to the n minus 1 becomes x to the n minus 1. And then how many of these terms did we have?
N.
We had n of them. We had one for all the numbers from 0 to n minus 1. How many numbers are there from 0 to 9? 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10 numbers.
Yeah.
Gotcha.
Okay, so there's n of those. So it is equal to n times x to the n minus 1, which is what we were after.
All of those turn into x to the n minus 1?
Every single one of them, because their exponents always sum up to the same number. The x's exponents count down, and the z's exponents count up.
Okay.
And so when you add their exponents together, they always come out to n minus 1.
Okay. That's cool.
Looking at it right here, here's a concrete case. All the exponents are going to add up to 4.
Yeah.
And how many numbers do I have listed out there? How many terms? 5.
That makes sense.
Okay, so with that, let's do some concrete examples using the rule now. You should be able to kind of just do these in your head now. What's the derivative of x cubed?
It's going to be
3x
x cubed power 3 times x squared.
Bring down that 3, so that becomes 3 times x. Now it's to the n minus 1 is now 2. So you bring down the n, pull it in front, and then decrement your exponent by 1. Okay, let's try another one. X to the square root of 2. What is that?
Square root of 2x square root of 2 minus 1.
It's just the square root of 2 times x to the power of the square root of 2 minus 1. Whatever that is. Glad. Good. You didn't overthink it.
That's what I did that.
All right. Let's try this one. X to the negative 4/3.
Negative
4 thirds
x.
x.
Negative 4/3 x to the power of.
You could.
Negative
1 third.
7 thirds.
1 third.
Minus 7/3. You subtract 1.
Oh. Yeah, that's right. Shoot. Okay.
Good? Let's try this one. X to the 2/3. What's its derivative?
2 thirds
X
x.
to the power of negative
negative
1 third.
5.
Minus 1/3. 2/3 minus
Oh,
1
I
is
keep mixing it up. I can't
negative
keep it.
1/3. So bring down the exponent, then subtract 1.
Subtract.
All right. What's the derivative of 1 over x to the 4?
1 over 4x to the power of 3.
It's what?
1 over 4x to the power of 3.
No.
Isn't this the quotient rule?
We could have used the quotient rule, but we're not to that yet.
Oh, it's gonna be, you're gonna, how do you do that again? That's the same thing as x to the square, x squared, isn't it?
I thought you had it
Isn't
for a
it
second.
1
that
to
not-
the power of
1 over
negative
x is
3.
the same.
So this is the same thing as x to the power of negative 4. What's x to
Oh,
negative 4?
duh, that's right.
It's 1 over x to the 4.
Oh man, that was.
Okay, so now what's the derivative of this?
Negative 4x to the power
To the
of
power
5.
of 5.
To the negative 5.
Yeah.
Or that's the same thing as negative 4 over x to the 5. Same thing.
Which one is more formal?
Depends on context.
It doesn't really matter.
Sometimes one's more useful, sometimes the other. I would say that this is slightly preferred, but there's lots of context where this is perfectly appropriate. Alright, now the grand finale. What's the derivative of the square root of 2 of x to the 2 plus pi?
The square root is the same thing as power.
Wouldn't it be
Perfect. So this is the same thing as a derivative with respect to x.
just
Of
root
X.
X
pi?
to the 2 plus pi
Times 1/2.
times 1/2.
So that is going to be 1. So it's going to be x to the power of.
Oh, that's right.
So it's going to be x to the 1 plus pi halves.
Which is going to. Yep.
Now we can take the derivative. What's the derivative?
1 plus pi half x.
Doesn't
1 plus pi
become
halves.
0?
All times x. Don't forget your parentheses.
Oh,
Yeah,
that's
to the
why.
power
it
of
does it.
pi halves.
Okay.
Bring that down
And
to the
then
power of pi halves.
gotcha.
And we can mess with that a little bit more if we want. I can reinterpret that halves as a square root, and we can call this 1 plus pi halves times the square root of x to the pi.
To the pi.
To the pi, not the 5. No clue why I wrote that. Times the square root of x to the pi. Make sense?
Yep. Makes sense.
Okay. And imagine trying to plug that thing into that and figuring it out.
You would have to use the derivative.
Be really hard.
Yeah, become messy. So now we can calculate derivatives like that. Hardly even have to think about it.
Sweet.
Told you you'd be able to do these in your head, no problem. Okay. And after this, the only other thing you have to learn how to do is integrals. And then you know calculus. I mean, you're basically there, right?
Are we? Is it really that much simple?
It's not as scary as people make it out to be. But yeah, I wouldn't say it's simple. Still have a lot of hard work ahead of you. Okay. Moving forward. So let's prove our next rule. So let's see. We've done this rule, so now we're doing this rule. Prove that the derivative of a constant times some function is equal to the constant times the derivative of the function.
Oh,
We're proving each of those rules. I just want to give you
I was
intuition
wondering
first.
why we were only using the power rule down there.
Okay, yeah. I wanted to give you all the rules, give you intuition for them, then prove them as we go, and do examples using each rule.
Yeah, that makes sense.
Okay, so the next one. So if u is some function in terms of x, then the derivative with respect to x of c times u is equal to c times the derivative of u with respect to x. You can pull the c outside the derivative.
Gotcha.
C is a constant, u is a function, right? So let's prove it. So let u be some constant, or be some function in terms of x, and let c be c in the real numbers, meaning c is any real number.
Yeah.
Pi square root of 2, whatever, any real number. Then, what is the derivative with respect to x of c times u? Well, using this definition, doesn't really matter which one we use, just pick one. So using this definition, that is going to be c, plug in x plus u into that thing, you get c times f of x plus h, or plug in x plus h, right?
Yeah.
Into that gives you this, minus plug in x to that gives you this, all over h, the limit as h approaches 0. Make sense how we just plugged into the definition? Just blindly plugging it in.
Alright, wait. Where's your u?
U is f of x, same thing.
Oh, I see that.
I could have just as easily called this u of x plus h if you wanted. I just afraid that if I didn't have an f there, I might confuse you.
No, that makes more sense.
That makes more sense? Okay. So, just plugging into the definition, right?
Yeah.
Now, what do we know? We know that the limit of a constant is equal to a constant times the limit. Going back to our limit laws. So from our limit laws, we know that we can pull constants outside of limits.
Yeah.
And so using our limit laws, we pull the c out. We can factor the c out of both those terms and then pull it out using our limit laws.
Okay.
And then what is the limit as h approaches 0 of f of x plus h minus f of x all over h?
It's du over dx.
That's exactly what we mean by the derivative of u with respect to x.
Yeah.
That's exactly what that is. That is du dx.
That's it.
That's it.
Okay.
Pretty straightforward. Plugging into the definition, use the fact that we know we can factor constants out of limits. Look at the limit.
Okay, that makes sense. Well. Yeah.
Okay, straightforward. So now, what's the derivative with respect to x of pi times x cubed?
Wouldn't it be pi times derivative?
Yeah, it's pi times the derivative of x cubed. What's the derivative of x cubed? 3x squared.
I see.
Bring down the exponent, decrement the, that's it.
2pi squared.
Gotcha.
Let's try another one. What's 12 times x to the negative 3? Its derivative.
The same thing. 12x.
It's 24x
So,
to the negative 4.
Well,
you guys are both saying different things.
It's 12
But now it's not.
times x
12 times x,
to the power of negative 2.
that's definitely
And
not
then
right.
You gotta put your negative 3. So negative 3 times
Oh, yeah, negative
12.
So you're saying 12 times negative 3 times what?
X.
times x to the power of negative 2.
Negative 4.
Negative 4. Subtract 1.
Oh. I don't know how to do that.
We're not getting it closer to 0. We're always subtracting 1.
Subtract.
Or in other words, it's equal to negative 36
Is
times
that
x
right?
to the minus 4. Yes, that's right.
Makes sense.
Okay, next proof. Proof that the derivative of a sum is just the sum of the derivatives. And this is, again, going to use our limit laws. We already know that the limit of a sum is the sum of the limits. That's going way back to like our second class or whatever.
Yeah.
So that's all we're basically using here. That's why it's such a short proof. And right here, square box. So, let u be some function in terms of x, let v be some other function in terms of x. Then we're going to prove that the derivative with respect to x of u plus v is the derivative of u with respect to x plus the derivative of v with respect to x. Make sense what we're proving?
Yeah.
Alright, let's plug in the definition. What is the derivative with respect to x of u plus v? It's what we get when we plug x plus h into u and v. So x plus h into u, x plus h into v.
Oh, okay.
So I plugged x plus h into this function. It's right there.
Yes.
Minus what we get when we plug x into this function.
Yeah.
So minus x from this, and then minus v from this.
Okay.
Good so far?
Yeah.
That's just flat out plugging in to the function in the definition.
Okay, I see. Okay, I see that.
Everything's good?
Yep, we're good.
Okay, from here on out, I'm just going to group my terms a little bit different. I'm going to move this negative f of x and pair it with this. I'm going to move this negative g of x and pair it with g. So I'm just going to rewrite it like this and like this. We can think about it all over h for a second if you want. No, I didn't lie. Okay. So this, going from here to here would just be regrouping, right? And then I can write it as two separate fractions. 1 plus 3 over 4 is the same thing as 1/4 plus 3/4.
Yeah.
So I'll write it as two separate fractions and add them together. Okay, perfect. Now, what is the limit as h approaches 0 of f of x plus h minus f of x all over h?
That's,
G of u.
It's the derivative of u with respect to x. That's its exact definition. And similarly, what is the limit as h approaches 0 of this? Right, so we know that the limit of a sum is the sum of the limits, so I can take the limit of this and add to the limit of that, which gives me du plus dv.
Okay.
also one line group.
Yeah, pretty simple. Okay, so let's do some examples of this, or an example. I give you y is equal to 4x cubed minus 3x squared plus pi x. And I want you to find y prime, or find the derivative of this thing with respect to x. How do you do it? We can just take the derivative of this, add it to the derivative of this, and add it to the derivative of this.
Which is
That's what we just showed up here.
just the power rule.
And so, when we take the derivative of this piece, what do we get?
12x squared.
12x squared, just bring down the 3. So 3 times 4 is 12, and then we only have 2 left. So 12x squared
Negative 6x.
minus 6x.
And then plus. Wouldn't it just be the same? Negative that.
Pi.
Not pi.
You have negative 1 up there, or you have 1. Oh, it'd be 0.
It'd be pi.
We got pi's and zeros.
The derivative
Look,
of x
it's
is 1.
it's
You
1.
can think about it as pi times x to the 1. Bring the 1 down. So
So
1
it's
times
just
that,
that.
and decrement it to 0.
Which is 0.
What's x to the 0?
1.
It's 0. So this whole thing's 0.
I was right.
No, it's 1. X to the 0 is 1. So it's pi. Anything to the power of 0 is 1. It's not 0.
Okay.
Okay.
You know that when you multiply terms together, you add exponents, right? Let me help you with this really quick. So if I have a to the 3 times a to the negative 3,
You add exponents.
then this is equal to,
1 apparently.
well, it's equal to a to the 0. You're good with that, right?
Yeah.
But a to the negative 3, this is the same thing as saying a to the 3 over a to the 3.
Oh, that's right. It is.
So that's the same as that. This is obviously 1, and so that's 1.
That helps.
Okay. So x to 0 is 1, and so you're left with 1 times pi, which is just pi. And it wasn't positive or negative, it was positive. You follow that?
Yeah.
Okay. Now let's prove our product rule. Now we already know that the limit of a product is just a product of the limits. So the derivative of a product is just a product of the derivatives. No. It's this whole thing. It's not just du dx times dv dx. It's a sum of two things. So this is not obvious. In fact, Leibniz had in his journal when he was driving calculus, he said something like, and obviously the derivative of a product is a product of the derivatives. And then he realized he made a mistake and he fixed it. But since he wrote that in his journal, we actually have it recorded for a second he thought that. So even great minds got confused a little bit by this. So you have to memorize what exactly this is. And what's the mnemonic we use? We say the first times the derivative of the second plus the second times the derivative of the first. So that's the mnemonic you're going to memorize. So that's writing out with U's and V's. Writing out with F and G's, just so that you can see it two different ways, because they show up pretty commonly in both these formats. So I just wanted to show you both. The derivative with respect to x of f times g is f of x times g prime of x. The first times the derivative of the second, plus the second times the derivative of the first. Different notation, saying identical things in both cases. See it?
Yeah.
Okay.
Okay, so now let's prove it. So, what is the derivative with respect to x of f times g? Well, I need to plug in x plus h into both these functions. So just using the definition here, which one did I use? I did h going to 0, so we're using this definition. So plug in x plus h into this function. This function is f times g, that's our whole function.
Yeah.
So I get f of x plus h times g of x plus h. That's plugging in this piece. Minus, when you put x into this function,
Yeah.
all over h, taking the limit as h goes to 0. So that's just plugging in the definition. Okay, now, what is this? We are going to, just out of the blue, because we feel like it, I'm going to subtract this term and add it again. So the only difference from here to here is I subtracted this and added it right back in.
Okay.
Make sense? So no cheating, right?
Yep.
Now, what am I going to do? Notice that these two terms have a f of x plus h in them. So from these two terms, I'm going to factor out that f of x plus h.
Okay.
And so I'm left with g of x plus h minus g of x.
Okay.
And then it's still all over h.
Right.
Same thing over here. Notice both these terms have a g of x in them. So I'm going to factor the g of x out of them. And so I have an f of x plus h minus f of x all over h.
Which is the same thing as your derivative.
which is the same thing as my derivatives. That's my whole problem right now. Maybe hammer that home a little bit. Going all the way to the top, why can't I just take the limit of this thing? Because there's an h in the denominator and I don't know what to do with it.
Yeah.
Well, if I can split it up in such a way that gives me derivatives of things,
That's easy.
that will get rid of my h's. So now when we're right here, we know what this limit is and we know what this limit is. This limit is the derivative of g. This limit is the derivative of f. So we get,
Of h.
take our limit now as h approaches 0. What is f of x plus h as h approaches 0?
FX.
F of x, because the h goes to 0. What is g of x plus h minus g of x over h as h approaches 0? That's exactly what we mean by the derivative of g. What is the limit of g of x as h approaches 0?
G of X.
It's just g of x.
Times f prime.
And then this is just the derivative of x, or the derivative of f. Make sense?
Yes.
Okay.
And so that's what we got. We got the first times the derivative of the second plus the second times the derivative of the first.
Yep.
Now let's see this in action. So I give you this problem. We're going to solve this two different ways. One way I can solve this is I can multiply it out and then just use our power rule. And another way I can solve it is to use this product rule. We're going to do it both ways.
Okay.
So first, let's just write it out. And we're doing it both ways so you can see they give the same answer. So y is equal to, distribute the x squared to everything. X squared times x cubed is
Power rule first.
x to the 5. X squared times, well, let's do the 1 next. 1 times x cubed is
X cubed.
x cubed. X squared times 3 is,
3x squared.
and then 1 times 3 is,
That's 3x squared.
Yeah, 3x squared.
oh, thank you. All right, everything there look good now?
Yes.
Yes.
Okay, now let's take its derivative. What's the derivative of this?
It's 5 times 5x4.
5x 4.
5 times x to the 4. What's the derivative of this?
3x2.
3x squared. What's the derivative of this?
6x. 6x.
Just 6x.
Oh, yeah.
And what's the derivative of 3?
0.
0, so we don't mess with it. So there's our answer, right? Now I'm going to redo this problem using this rule.
Okay.
So what is y prime? It's the derivative of the first, or sorry, it's the first times the derivative of the second. What's the derivative of this?
Is 2x. Is 3x2.
0. Yeah, 3x.
3x squared plus 0.
Yeah.
Right?
Yeah.
So we just really did the first times the derivative of the second plus
Second.
the second times the derivative of the first. So what's the second? That's x squared, x cubed plus 3. Now times the derivative of the first. What's the derivative of this?
It is
2x.
Just 2x. Right?
Yeah.
Now distribute it out. X squared times 3, x squared is 3x to the 4. 1 times 3x squared is plus 3x squared.
Yep.
X cubed times 2x is plus. Did I do that right?
Let's find out.
2x to the 4. And then 3 times 2x is plus 6x. Alright, so combine like terms, 3x and 3x to the 4 plus 2x to the 4 is 5x to the 4
Plus 3x squared plus 6.
plus 3x squared plus 6x. Is that the same?
Yep.
And it worked.
So
Ta-da.
Okay.
Now you might be thinking to yourself, why would I ever use a product rule when multiplying it out first was way easier?
Yep.
And that happened to be the case with this problem. It's going to be some problems, it's obviously way harder to do one way and way easier to do another way. So it's good to have all these tools under your belt.
Okay.
And so there's kind of an art to it about which rule is the right rule to use. And you kind of just got to get a feel for it and kind of see, oh, that one's going to become a pain because of this thing or that thing. So there isn't, here's the rule you should use. It's just sometimes it's going to be easier, sometimes it's going to be harder. Okay. Now we got to prove the quotient one. Here's the bad one. What's the derivative with respect to x of u over v?
It's
It's the bottom one times the derivative of the top minus the top one times the derivative of the bottom all over the bottom squared. What are you going to memorize? low d high minus high d low, square the bottom, and away we go. And that will be your mnemonic. Let's prove it. So we want to find the derivative with respect to x of f of x over g of x. Right? So what is the derivative with respect to x of f of x over g of x equal to? We're using it as h goes to 0. So we gotta plug x plus h into our function, and then subtract what we get when we plug x into our function. So when I plug x plus h into this, what do I get? I get f of x plus h over g of x plus h.
Yep.
Now I've got to subtract what I get when I plug x into the function, which gives me f of x over g of x,
Yep.
all over h.
Yep.
You with me? Now I need to get a common denominator in the numerator. So I'm going to multiply this one top and bottom by g of x. I'm going to multiply this one top and bottom by g of x plus h.
Okay.
So that's all we're doing here. So we get a common denominator in the numerator.
Okay.
Good?
Yeah.
Now, write these two over the same denominator. And dividing by h is the same thing as multiplying by 1 over h. Just rewriting it like that for a second so I don't have to think about it as a fraction over a fraction.
Okay.
So just so that my notation isn't too messy. Okay, now I'm going to do a similar thing that I did last time. I'm going to, so here's this term. I'm going to subtract f of x times g of x. I'm going to add it back on over here.
Okay.
Okay.
So I subtracted it and I added it. They cancel out to 0. So I didn't cheat. I didn't change anything.
Okay.
You with me?
Yep.
So this term is right here. Minus this plus that, and then this term is right here, all over the denominator, and then rather than having h to the side there, multiplying by 1 over h is the same thing as dividing by it, so just stick it in the denominator down there. With me?
Yep.
Okay. Now I'm going to split this up into two separate fractions. I'm going to group these two terms together, and I'm going to subtract these two terms.
Okay.
Okay? So these two terms, they're just right there. Nothing tricky there with their denominator. Now, minus this thing is right there, but I've also factored a negative out of this, so now that's a minus.
How did you factor the negative out?
Well, distribute your negative back in. Negative times this gives me negative that. Negative times this gives me positive.
Oh, gotcha.
So I just pulled the negative out of this term and pulled the negative out of this term and stuck it out there in the front.
Okay.
And then the denominator is still the same. You with me?
Okay.
Now I'm going to factor g of x plus h times g of x out of both these terms and just move it to the front.
Okay.
Good there? And still just leaving the h. On top of that, I'm going to factor a g of x out of the numerator here. There it is. I'm going to factor an f of x out of the numerator here. There it is.
Okay. That makes sense.
Good? And now, just rewriting this now in the denominator. Multiplying by it is the same thing as dividing. I just didn't want to work with a triple fraction the whole time. Okay? And now we're ready to take our limits. What's the limit of g of x as h approaches 0? G of x.
Yeah.
Can you restate that?
What is the limit of g of x as h approaches 0?
Oh.
It's just g of x. It doesn't depend on h in any way.
Yeah.
Okay, so g of x is g of x. What's the limit of this as h approaches 0?
The derivative.
That's the derivative of f.
F prime of x.
Minus is minus. F of x is f of x. I, for some reason, didn't finish writing my terms here. This was g of x minus g of x right there.
Yeah.
Sorry about that.
We're good. And then that's the same.
And then that becomes g prime of x.
Oh, that's easier to see.
And now, our denominator, as h approaches 0, what is g of x plus h? G of x. And what's g of x? G of x. So there it is. You see it?
Yep.
Now, write it slightly different. That's g of x times f prime of x minus f of x times g prime of x all over g of x squared.
That's easy to memorize.
the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Let's practice this. So now I've got t squared minus 1 all over t cubed plus 1.
Okay.
I want to calculate its derivative. What's its derivative?
Should we do the power rule first? Or can't we?
No, you cannot do the power rule and then try and somehow plug it into there. You'll do the power rule as you calculate the derivative of the top and as you calculate the derivative of the bottom.
That's what I'm saying.
Okay, but you can't like reduce this by doing power rules first and then plug into the formula.
Oh,
Because the derivative of the quotient is not the quotient of the derivatives. It's this thing.
yeah, okay.
Okay, we.
Okay, so what do we write first?
You're gonna write the
T of 2.
bottom times
The bottom function, whatever the bottom function is. So this is t cubed plus 1. The bottom times the derivative of the top. What's the derivative of the top?
2t.
2t minus
0.
0, so just 2t. Good. So the bottom times the derivative of the top minus the top,
2t minus 1.
t squared minus 1,
Or, yeah. And then,
times the derivative of the bottom,
which is 0, 3t squared.
3t squared, all over the bottom squared.
You don't need to. Oh.
You gotta square the whole thing.
That's it.
Well, then you simplify, and the answer is what the answer is.
How would you simplify?
That's what we would call the Alexander answer. So, multiplying it through, we get 2t to the 4 plus 2t. 3t squared times t squared is 3t to the 4, make it negative. And then negative 3t squared, make it negative, is plus 3t squared. Right?
Yeah.
All over the denominator, we can leave it as is. That's as simplified as it's going to get. You usually don't want to expand that out unless you have to. The reason you're expanding these out is because most likely some terms are going to cancel and collapse.
Can you factor anything on the bottom? Can you expand it out?
It's already factored. It's t cubed plus 1 times t cubed plus 1.
I mean, can you factor from the top? Like, can you reduce
Couldn't you have canceled out that first one on the left? First.
No, because this isn't a common factor. It has to show up in everything in the numerator if you're going to cancel it out.
Alright.
I cannot say 2 plus 6 over 2 is 6.
Yeah. Okay, gotcha.
Alright, so this is equal to, how many t's to the 4 do we have? 2 and negative 3 here gives us minus t to the 4. And then we have plus 3t squared plus 2t. All over t cubed plus 1 squared. Make sense?
Sense.
So, taking derivatives of quotients is in general a messy process. Doesn't come out clean. We don't like when we have to do it, but it's not too bad.
Okay.
Okay, let's do one more. Let's find y is equal to x cubed minus 3x squared plus 2. Let's find its fourth derivative.
This isn't a quotient.
This isn't a quotient.
Okay.
So this last one is to make sure we understood this notation here. Right? Just going down.
Okay.
all those
Just doing it 4 times.
Okay, so yeah, let's find the first derivative. So what's y prime equal to?
3x squared
3x, yeah, 3x squared.
minus 6x.
6x. That's it.
That's it. So there's our first derivative, but we're looking for the fourth derivative. So now we take the derivative again. So it's y squared. What's the second derivative now? That's the derivative of the derivative.
6x minus 0, 1.
Minus
1.
6.
No. Oh,
Minus 6.
Minus 6,
Because x is 1.
because x is 1. Okay, now let's take our third derivative,
6.
6. Now our fourth derivative is finally
0.
0.
Oh, gotcha. Okay.
Good?
Is there an easy way you can tell when the derivative is 0?
Yes. This is only a third power term. If we take its derivative 4 times, we're guaranteed to be 0. If we took its derivative 3 times, we'd be guaranteed to be a constant.
What if you take it?
And in this case, it would be 1 times 2 times 3, which is 6.
Gotcha.
So yeah, you can start to see patterns like that. All right, no more questions on this board.
We're good.
Off to the next board.
I've got to leave at 2:45.
All right.
Is this supposed to be quicker?
I don't know. I would guess, but that's kind of up to you guys.
Why do we have to guess faster?
Okay, got that. So now we're moving on to the next section. The next section is on rates of change. Viewing derivatives as rates of change. We already have done this way back in the beginning, reintroducing it to you again. Give you a feel for what these types of problems are going to be like. This, homework-wise, is probably going to be one of the hardest sections you came across in terms of how hard the problems are. I think it'll only give you a few problems, but they're going to be harder problems because you're going to have to internalize a problem. You're going to have to do physics type thinking. Think about what's physically going on and how to represent the problem mathematically. So let's give you a quick example. I say, so here's some function representing the area of a circle as a function of its radius. Right? Imagine I had some stretchy circle. As I stretch out its radius, its area gets bigger.
Yeah.
Right? So now I want to know, how is the area changing with respect to the radius? Right? So I'm looking at the change in area with respect to the radius. As we make the radius bigger, the area also increases. If we were to graph this as a function of its radius, it would be some sort of half of a parabola. Why only half a parabola? Because there's no such thing as a negative radius.
Oh, yeah.
So that doesn't make sense, right?
Right.
But it would look like half a parabola like this, right?
Yeah.
Where when its radius is 1, its area is exactly pi.
Yeah.
And when its radius is 2, then its area is 4 pi, etc. With me?
Yeah.
Okay, so what is the change in area with respect to r? That's asking what is the change in A with respect to r? What is dA dr? What is the derivative of A with respect to r? And in this case, what is it?
2 pi r.
It's just 2 pi r. 2 pi r is the derivative of A with respect to r.
Oh, okay. Yeah.
This is how the area is changing. The units here would be meters squared per meter, so it comes out just meters, but meter squared per meter is how you think about it. How much is the area increasing per meter of radius? It's giving us the change in area with respect to the radius. Right?
Good.
Yeah.
And so, pictorially, what does that give us? Exactly what you think. It gives us the slope of the function at any point. And so the question then says, how is the area changing with respect to the radius when the radius is 5? That's identical to asking, what's the derivative of the function at the point 5? And what is it when we plug in 5 for the radius?
10 pi.
Yeah, bye.
10 pi, never forget your units here.
Meters.
Yeah.
Meters or meters squared per meter, I think helps you see it better.
How do you get 2 meters?
Meter times meter here,
Oh, because how?
it's
Pi is meters and r is meters.
area is meter square, radius is meters. So meter squared per meter,
Okay.
which is just, you can do cancel out your meter stopping bond, but it kind of causes you to lose track of what's going on in the problem.
Okay.
So there's a really weird problem for you that the math, stupid simple. The hard part here is going to be for you to understand what it's asking you to do. And that's how you're going to fill in these problems. How on earth do I set up this problem? Where do I even start? And that's going to be the hard part. So let's introduce some definitions and then do a problem that we've already introduced twice, I think. So definitions. let s of t be the position of an object at some time t. So this is just giving me the position of some object at a particular time. And you can just graph it out.
Okay.
Right? So if I were pacing back and forth, and we were graphing my s of t, it would look something like this. I start out here, and I'm going up and turning back, and going up and turning back. If this is my 0, I go up to 5, and then I turn back and walk back. There's my position with respect to time. Okay. So, let s of t be the position of an object at some time t. Then the displacement of an object from some time t to some future time t plus delta t is given by the position at the end time minus the position at the start time. If at t, I'm at position 3, and at t plus delta t, I'm at position 5, what's my displacement?
2.
2. Most likely 2 meters if we're counting in terms of meters, right?
Yeah.
So, s of t plus delta t minus f of t, this gives you your displacement.
Okay.
And our average velocity then is displacement over time. Right?
Yep.
Good with that?
Yep.
So, this is our average velocity. What is our instantaneous velocity then?
It would be at
When delta
2.
t is 0.
It's going to be the limit as delta t approaches 0.
Okay.
So, velocity is, by definition, the derivative of position with respect to time. Or in other words, it's the limit as delta t approaches 0 of your displacement over your time.
Instantaneous.
That's your instantaneous velocity, which is what we always mean by velocity. We'll either say average velocity or velocity.
And velocity always refers to instantaneous.
Yes,
Even for my physics course.
it should.
Okay.
Okay, now speed is the absolute value of velocity, so it's the absolute value of ds dt. Huge difference between speed and velocity. There's no such thing as a negative speed. There is such thing as negative velocity.
Direction.
Let me give you, velocity takes into account direction. Speed does not. So if I sit here and I walk at 5 meters per second for 2 seconds, and then I walk at negative 5 meters per second for 2 seconds,
The speed.
what was my average velocity?
0.
0. What was my average speed?
5.
5 meters per second.
Yeah.
So velocity and speed are two different things.
Just distance. Or direction.
Yeah, velocity takes into account your direction. Speed does not. Speed doesn't care which way you're moving. Good?
Okay.
Okay, acceleration. By definition, what's acceleration? It's the derivative of velocity with respect to time. It's how your velocity is changing. If I have positive acceleration, that means I'm speeding up. If I have negative acceleration, that means I'm slowing down.
How do you do that in respect to instantaneous velocity?
What? You can think about average acceleration is your change in velocity over time. And so what is acceleration? It's your instantaneous change in velocity.
Over instantaneous time? Or
Not over anything. It's just instantaneous at a particular instant. Oh, did I say something weird? Let me say it again. Your average acceleration would be your change in velocity over time.
Yes.
If at 1 second, if I'm going 5 meters per second now, and then in 2 seconds, I'm now going 15 meters per second, what was my average acceleration?
Yeah, but
I increased 10 meters per second in 2 seconds, so my average acceleration was 5 meters per second squared.
But how do you take that into account? How do you determine the velocity over that time? Is it the average velocity they're referring to?
Your velocity at one point, minus your velocity at the end. It's this exact same thing, just replace your s's with v's.
It's delta.
Right, that's some delta t.
Okay. I see that now.
Okay,
That makes sense.
so acceleration is just the derivative of velocity with respect to time, or it's a second derivative of position with respect to time.
Okay, gotcha.
Similarly, jerk is just the derivative of acceleration with respect to time, or the second derivative of velocity with respect to time, or the third derivative of position with respect to time.
Okay.
Right? Big bang jump. Don't be a third derivative of position with respect to time.
Don't be here.
Don't be a jerk.
Is that what Sheldon says?
Yeah. Okay. So there's some definitions. Now let's go back to the problem that we talked about over and over again. It is an observable fact that objects close to the surface of the Earth accelerate downwards at 1/2 g times t squared. This gives me the acceleration of some object. Or sorry, this is its position.
At free fall level.
As it falls through the air. This is the equation we've already been using, where g is just some constant. If g is in terms of meters, then it's 9.8 meters per second squared. Those are just the units. And if g is in terms of feet, then it's 32 feet per second squared.
G isn't just some number, it's gravitational force.
Yeah, but it's a constant.
It's a constant number, but it's not just a random number.
I didn't say it was randomly chosen. It's an observable fact that it is this number. Objects accelerate downwards close to the surface of the Earth at 9.8 meters per second squared, or at 32 feet per second squared. That's what g represents. So this tells me where an object is that's in free fall.
Okay.
T seconds after it starts falling. It tells me how far it's moved. You with me?
Yeah.
Okay. So let's have the problem again. A ball is dropped at time t equals 0. So I take a ball and I let it go at t equals 0. I'm standing on the edge of the Empire State Building or whatever. Dropping the ball off. Question. How far does a ball drop in 3 seconds?
399 times.
Now we've got to pick, are we going to do this in terms of feet or are we going to do this in terms of meters? Let's do this one in terms of meters. So the position of my ball, S of t, is given by 1/2 g. If we're doing meters, g is 9.8. Half of 9.8 is
Something.
4.9 times t squared. So there's the position of my ball after t seconds.
You sure it's 4.9?
What is half of 9.8?
Oh, done. Okay, gotcha.
What's half of 98? 49.
Yeah.
Oh, that's such a good way of thinking about it.
Okay, so question, and this is in terms of meters, since we chose this one right here.
Yeah.
Okay, so it's in terms of meters. Question, how far does it fall in 3 seconds?
9 times 4.9.
9 times 4.9. So S of 3 is equal to 9 times 4.9. What's 9 times 4.9?
44.1 or something.
Which 9 times 9?
What's 9 times 5?
9 times 5 is 50.
You can think about it as 50 if you want.
Oh, 54.
What's 9 times 50?
It's
45.
450.
450. Now subtract 9.
It is
441.
441. So,
Check.
What the heck?
5 times 9, 5 times 0.9 is equal, or 5 times 9, yeah. So pretend that that was a 5. 5 times 9 is equal to 45. But then we counted
Oh,
an
that's
extra 0.1 more than we needed to.
right.
Oh, did I subtract a 0.9?
Yeah.
We counted one extra what?
Point.
Now I'm thinking about it weird.
Strange time.
49 times 9, and then subtract 1. I think I did that right. You can multiply it out if you want. Pretty sure that's right.
You should multiply that.
I'll do it.
Okay, so now that is how far the ball falls after 3 seconds. What's next? Next, they want us to find the velocity, the speed, and the acceleration at 3 seconds. So after 3 seconds, how fast is the ball moving down? So we need a velocity function. How on earth am I going to find a velocity function for this thing?
Take the derivative of your speed function.
Exactly. Velocity is just a derivative of position with respect to time. This wasn't your speed function, that was your position function. But yeah, so what is the derivative of this?
Couldn't you do displacement over elapsed time? Which is the same thing.
What's the derivative of this with respect to t? So v of t is equal to ds dt. Okay. What is ds dt when this is our s?
It's It's 4 points. It's 0.
9.8, that's where we got that 4.9, was half of 9.8.
Oh, yeah.
So 4.9 times 2 is 9.8 times
T.
t. So what is our velocity at 3 seconds?
9.8.
Oh, are you doing the derivative of st?
Not right.
Yes, velocity is a derivative of position with respect to time. Did we mess something up?
Doesn't seem right.
What doesn't seem right?
That just doesn't feel right. I don't know.
Isn't it 9.8 over
So
0? Wait.
98 times 3 is going to be 300 minus 6 is going to be 2.9 or 29.4
Okay, that makes sense. Okay.
meters per second is our velocity after 3 seconds.
Okay.
Why are you?
That's not equal to that, but that's, so v of t is equal to that, or v of 3 is equal to 29.4 meters per second.
Why is your?
Because here's our velocity function, just plug in 3 and you're
Should
done.
it 9 point? Oh, never mind. Okay, I think we're good.
Okay, now we were supposed to figure out what is the speed at 3 seconds.
Speed is the
Speed is the absolute value of velocity.
So it should be.
Oh, so it's the same. Too.
So it's the same. Your speed is either going to be the same as velocity, or if velocity is negative, it's just going to be positive. Speed and velocity almost identical. When we talk about instantaneous speed and instantaneous velocity. Okay, finally,
Well, how is it going to be? What was in your example where you walked over and then walked?
that was your average speed
Oh,
over the time.
average versus instantaneous.
Right. Now finally, what is our acceleration at t equal to 3? Now from physics, you know that the answer is just g, right? G is our acceleration, but we'll see that that falls out of this. Because our acceleration at t is equal to the derivative of our velocity with respect to time, which is equal to, what's the derivative of this with respect to t?
9.8 times
9.8 times 1, or 9.8, and our units are meters per second squared. I don't expect you to be comfortable with those units, but that's the number.
Gotcha.
So there you go. So what is our acceleration at time equal 3? It's equal to 9.8. It's 9.8 no matter what. Our acceleration function is a constant function.
Wouldn't it be increasing every second in there?
The speed is increasing. The acceleration is the same.
Oh, it's pulling it down.
The acceleration is constant.
Okay.
Okay, so now with that, let's try your problem. A rock is blown into the air at 160 feet per second. Launched up, straight up into the air. Our job is to first find the max height the rock went. Then we need to find its velocity and its speed when the rock is 256 feet in the air. Then we need to find its acceleration. And then we need to find out when the rock lands.
Crazy.
Right? So we got a rock, it's launched straight up in the air. Notice what's going to happen if we were to graph this rock's height with respect to time. What does it look like? The rock is going to shoot up in the air, slow down, slow down, slow down, slow down, stop, and then come back down.
It's gonna be a problem.
So if we graphed its height with respect to time, then it's going to make out a parabola. Okay, so first thing we want to do is we want to figure out this thing's max height when it's right here. Well, first off, let's talk about the position of this rock with respect to time. Let's talk about what is our position function going to look like.
0. It starts at 0.
It starts at 0, so if you plug in 0, we better get 0. But it starts out launching up every second. How far up is it going?
160.
160 feet up every second, right? So it's going up 160 feet every second. However, gravity is pulling down on it.
Negative 9.8.
Not negative 9.8. So here's gravity pulling down on it, negative 32 times t squared.
Using feet.
Because we're using feet. So this is going to be minus 32
That's,
t squared.
what do you get the t squared?
Slowing it down. Because, look, this is if it was just in free fall. If it was just in free fall, our position function would be s of t is equal to, if we're calling the down direction now negative and up positive, it would be negative 32 t squared.
Right.
Up here, we were calling our down direction positive. So this was doing it with meters. This is the exact same equation
That's tricky. Okay, I got you.
with feet.
Yeah.
Except for now we're calling up positive and down negative. So that's the flipping sign.
Which is
And now we have a difference that we start out launching upwards at 160 feet every second, but gravity is still accelerating us downwards at negative 32 times t squared.
Why is it negative 32 instead of negative 32 times a half?
Because I messed up. Thank you.
oh,
Minus 16.
Where did that 1/2 come from?
This is a fact of physics.
It's a basic law.
It's not a basic law. You could derive this, but you need integrals to derive it. Where does it come from? Here's the observable fact. Acceleration is a constant, and it's equal to g.
Yep.
Well, if acceleration is by definition the derivative of velocity, then velocity by definition is the integral of acceleration. And so your velocity function, v of t, is equal to gt plus some constant, depending on if you have some initial speed. In this case, we don't. And then now your position function is going to be, integrate that, you get 1/2 gt squared, and you learn how to integrate in your head. And then that's where the 1/2 comes from. Where does 1/2 come from? 1/2 is a thing such that when you take this derivative, you get that. Because the 2 comes down, cancel out with 1/2. So, we're not in physics, so we're not deriving these equations, but that's how we would do it. You can use your calculus to derive it. Okay, so max height. So I got the rock flying through the air. Here's its position with respect to time. What happens when the rock reaches its max height?
Then everything will be
Its
0.
speed is 0.
Its speed is 0. Its velocity is 0. So here's its position function. What is its velocity function? We'll write that right here. If this is its position function, what's its velocity function? What's v of t equal to?
Instantaneous velocity, though.
Yeah, that's what we always mean by velocity from here on out. We're never talking about an average change. Okay, so what's its velocity function now? It's just a derivative of this.
Derivative of s.
Just, what's the derivative of t with respect to t?
1.
Just 1.
Oh.
We're doing the derivative with respect
So
to
it's
t.
just 160. It's 160.
It's 160 minus, what's the derivative of t squared?
32.
Bring down to 2, so negative 16 times 2 is 32,
32.
and then t still to the 1. There's your velocity function.
Oh, is that it? What?
That's it, just take the derivative.
Okay, gotcha.
While we're at it, let's really quick get our acceleration function. What's our acceleration times t equal to? What's the derivative of a constant?
0.
0. What's the derivative of this?
32.
Minus 32. And so we're accelerating downwards at 32 feet per second squared.
Yep.
Okay, so now, back to our question. We're trying to find the max height. The max height is when our velocity reaches
0.
0. So when is our velocity equal to 0? So I want to know, when does 160 minus 32t equal 0?
What if they don't directly correlate? How are you supposed to figure that?
Well, let's see if we can figure it.
Okay.
What do you mean by directly correlate? I'm going to divide both sides of this by, can I see something that goes into both of them?
2.
2 goes into it. Can you see something bigger that goes into both of them?
4.
4 goes into both of them. Can you see something bigger?
32.
16 goes into both of them. Does 32 go into both of them?
No.
How many times does 32 go into 160?
None.
5.
How'd you know? So this is going to be 5 minus t equals 0. 5 times 32, 160. What's 5 times 30? 150. 5 times 2 is 10. 150 plus 10, 160.
And then you just add t both sides. So t equals 5.
So t equals 5. So t equal 5 is when it reaches its max height. 5 seconds later. Make sense? But we want to find what's the max height. Not when does it reach the max height, but what is the max height.
So you just plug it in.
So I just plug in 5 to our height function.
T.
So plug 5 into this, and what do you get? 160 times 5 is
800.
800. Good.
What?
You can think about that as 80 times 2 times 5. 2 times 5 is 10. 80 times 10 is 800. Minus 5 times 5 is
25.
times 16 is
How's that? 800.
We're on this one now. 25 times 16, 400.
160.
Look, 160 is the same thing as 80 times 2, right? You good? 160 is 80 times 2.
Yeah.
Times 5. What's 2 times 5?
10.
Times 80.
800.
There you go. You can do it in your head too.
Well, I'm doing it in the old school. Oh, I forgot to. What? 5 times 6 is 35.
5 times 6 is 30.
5 times 6 is 30.
Oh,
Times 1 is 5.
5 times 100 is...
Oh, I could have done it if I would have known that it was 5. Okay.
Alright.
Gotcha. I was on
So the max height is what?
800.
400.
400.
800 minus 400 is 400 feet. That's as
Where'd you
high
get
as it goes.
400?
400.
Oh. Gotcha.
16 times 25. If you have 16 quarters, how much money do you have? You have $4.
Okay.
Okay. So we figured out the max height. Okay. Now, we want to find the speed when it's 256 feet in the air. Now, when is it 260 feet in the air? Notice it's going to be 260 feet in the air right here and right here. It reaches that height going up and it reaches that height going down. So we're going to get two answers here.
Yeah, but it's just going to be the same thing negative.
So I want to find when the height is equal to 256. So when is 256 equal to our height function? 160t minus 16t squared. When does this equal 256?
We're solving for t, so...
And we're solving for the t. The time that gives us 256 is our height. And there's going to be 2 times it does it. First thing I'm going to do is divide both sides by 16. So I get 16 is equal to 10t minus t squared.
Is there a reason you did that first?
That's typically what you do.
Just subtract 160 first. We'll get the same answer.
Subtract 160. That's 160t,
Oh, okay.
right? That's times t there. With me? So I just divided it both sides by 16. That's all I've done so far. Okay, now I'll move everything to the left-hand side. So I get t squared minus 10t plus 16 is equal to 0. That's moving everything over here.
You moved your... Oh, okay, gotcha.
So the t squared becomes positive, the 10t becomes negative, and 16 is still 16. Now I factor it. What terms multiply together give me 16 and add together give me negative 10? Come on, don't make me do it for you. Two numbers multiplied together give me 16, added together give me negative 10. 4 and 4 gives me 8, so that can't work.
8 and 2.
8 and 2, positive or negative?
Oh, there we go.
Both negative. Negative 8, negative 2. Added together, give me negative 10. Multiplied together, give me 16. Okay, so what does t have to be to make this whole thing go to 0?
8.
8. So t equals 8 makes this equation true. And t equal to what makes it true? 2. So 2 seconds after you launch it, then it's 256 feet in the air. And then it goes up, up, up. At 5 seconds, it's at the top. And then after 8 seconds, it's back at 256 feet in the air. There's 2 points where it's 256 feet in the air. Right? And now we want to find the velocity at both those times. So what is the velocity now at 2?
Plug it in, pretty dead.
Plug it in. So 160 minus 64 is
96.
96. And then let's look at v at, what was our other one? 8. So now we've got, sorry, this one. 160 minus, let's see, what's 8 times 32?
36.
256, right?
What?
I'm not sure if that's what you said, but it sounded like you said 156. Okay. So I keep looking at S. We're looking at this one. So we have 160 minus 256, right? Which is equal to
Negative 96.
minus 96. So our velocity after 2 seconds was still going up at 96 meters per second. And after 8 seconds when it's coming back down, now it's going down at 96 meters per second. You with me? So that's our velocity when the height is this. What's our speed? What's our speed at 2 seconds? 96. What's our speed at 8 seconds?
96.
Still 96. It's the absolute value of your velocity. No such thing as a negative speed. Okay. So we did that. Our acceleration, what's our acceleration? Minus 32.
Yeah.
We already figured that one out. So acceleration is always minus 32.
Or
And when does it land? How long is this object in the air? Well, when it lands, what's its height?
0.
0. So we want to solve for when its height is equal to 0. So I want to know when 0 is equal to 160t minus 16t squared, right?
Okay.
Divide both sides by 16, just to help us see it. So that's going to be 10t minus t squared, right?
Oh, okay.
Okay, factor the t out. So what values of t make this thing equal to 0? 10 makes it equal to 0. And what else? What else can I plug into t to make it 0? 0. So notice those are the 2 times it's on the ground. At time 0, right before it gets launched into the air, and 10 seconds later it comes back and lands on the ground. So how long was the object in the air? 10 seconds. Because it takes it 10 seconds to get back to the ground.
Okay.
The height of the object was 0 at time 0, and it was 0 at time 10. Okay,
Oh, I see. Okay.
there we go. Quickie. 258. Should we leave the trig functions for next time? We can leave the trig functions for next time. It won't be too bad. Ooh, that also leaves a chain rule for next time. Let's do the trig functions and we'll leave the chain rule for next time. Trig functions are easy enough.
We try the whiteboard?
No. The whiteboard is just a bunch of examples using the chain rule. All right. Oops, I went too far. I don't care about the chain rule. I just care about the trig functions. Can I see them? Yes. Okay. So, trig functions. Taking the derivative of trig functions, what do we have? Here's what they are, and I'm going to quickly prove them for you. But the derivative of sine is just cosine. The derivative of cosine, just minus sine. Derivative of tangent, secant squared. Derivative of secant, tangent times secant. These are the derivatives of these functions. And so you're likely going to have to memorize those.
Yeah, I was going to say that's.
We're going to prove it really quick. So starting with sine. So I want to prove that the derivative with respect to x of sine of x is equal to cosine of x. Okay? Now, by definition, what is the derivative with respect to x of sine of x? Equal to. Using our definition, it's the limit. I'll use the one as h goes to 0. So it's limit as h approaches 0.
Sine inverse of sine?
Sine of x plus h minus sine of x all over h. That's the derivative of a function. It's the limit as h goes to 0 of what you get when you plug in x plus h minus what you get when you plug in x all over h. Good?
Yeah.
Now, we already did, going back to our trig review, sine of alpha plus beta is equal to what?
Beta plus alpha. Oh.
The sine of alpha plus beta was equal to
Cosine.
sine of alpha times cosine of beta plus sine of beta times cosine of alpha. You with
Wouldn't
me?
it be negative?
I think the sine adds, cosine subtracts.
Cosine's negative. Okay.
Okay, so we're going to plug that in for sine of x plus h. So this is going to be equal to the limit as h approaches 0 of sine of x plus h is the same thing as sine of the first angle times cosine of the second angle plus sine of the second angle times cosine of the first angle minus sine of x all over
It's not an angle though. H isn't it?
h. That is a radian, a number. Whatever you plug in there. Sine of the first thing. This thing doesn't say, I only work if alpha and beta happen to be radians that you read off of a chart somewhere. This is true for any two numbers, alpha and beta.
Angles specific.
Well, we use alpha and beta typically to be numbers, radians representing something, but they're just numbers. This always holds.
Okay.
Okay. So let's see what we can do with this. This is going to be equal to. What am I going to do with the cosine of h over h?
Cosine of h over h is equal to 1, isn't it?
No, that's sine of h over h. So I know that I can rewrite this as the limit as h approaches 0 of, this is why I should solve these ahead of time. Sine of h over h times cosine of h. So that's this term. What am I going to do with that sine of x?
Doesn't that get cancelled?
I'm missing something obvious. You canceled it with what?
The sine of x?
No, because that's a sine of x times a
Oh,
cosine of x. You
Isn't
can't
that
just get
supposed
rid of
to
it.
have a cosine of h? You have sine x cosine h plus sine h times cosine x, right?
Okay, you are onto something. Sine of x times cosine of h plus sine of h times cosine of x. Okay, yes, that was a problem. Okay, so I rewrote this term right here. Okay, so that should be a cosine of x, right? Okay, so now I still have these two terms. And that's how I get my minus 1. Okay, so plus, I see it now. So these two terms together, let me just write it before I factor out. This is sine of x times cosine of h minus sine of x all over h. So that is right here, and then these two together are right there. Do you see it? Sorry, jumping around with the algebra law on you.
I don't.
You don't? Okay. Let's break it up first up there, and then we'll break it up again. Sorry, I had to see where I was going first. Okay, so I want these two grouped together. So I'm going to write that as sine of x times cosine of h minus 1 plus sine of h times cosine of x all over h.
You get the 1.
Okay, so sine of x times cosine of h is right here. Sine of x times negative 1 is
Oh, okay.
good with this?
Yeah.
Now I'm going to split it up. We're still taking the limit of this, so the limit of this equal to, over here now, I'm just going to split it into two fractions. So this is going to be the sine of x, that's right there, times cosine of h minus 1 over h, plus, now this one is cosine of x times sine of h over h. And now we can take our limit. So now this is equal to cosine of h minus 1 over h, its limit as h approaches 0 is, you might not remember, but it was 0. These are limits that we already calculated for this one and this one,
Well, that one's
using the sandwich theorem. So yeah, this one goes to 0, and this one goes to 1. You with me? Sine of x times 0 is 0. And now, as h approaches 0, what's cosine of x?
cosine of x.
Still just cosine of x times 1 is,
Cosine of x.
and there it is. See it? Now let's do cosine. It's going to be a similar thing. So, let's look at the derivative of cosine now. Cosine of x. What does this equal? So it's going to be the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h, right? Okay, now using our rule for cosine, that was that the cosine of alpha plus beta was equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Good? Okay, so now, using that, then this is still, so we'll do the limit, we'll calculate the limit when we got it all done. So this is equal to cosine of the first times the cosine of the second minus sine of the first times sine of the second minus cosine of x. No mistakes?
You're saying,
Right? Make sure I didn't accidentally do an h twice so I can't see how to factor. Okay,
yeah, we're good.
now I know how to do sine of h over h. So I'm going to group these two together. And I know how to do cosine of h minus 1. So I'm going to group these two together. Maybe I'll write it like this and hopefully you'll see it. So I have cosine of x times cosine of h minus 1. That's this term and this term, factoring out cosine of x.
Nice.
And then we still have this term right here. So minus sine of x times sine of h.
All over it.
And then everything's over h. I'm just going to write as two separate fractions. Right?
Yep.
And now we know how to calculate the limit of this thing. So now when we take our limit, cosine of h minus 1 over h is going to give us
0.
0. So this gives us 0. 0 times cosine is 0. So that whole thing goes to 0. Over here, sine of h over h gives us
1.
1 times sine is
Sine of x.
sine, but negative, so negative sine. So it's equal to minus sine of x. That was the derivative of cosine. Good? Now that we did those two, the rest of these are very easy using our other rules. So,
If sine of x equals cosine of x, cosine of x equals negative sine of x. Sine of x equals negative sine of x.
you're not saying your derivative, so what you're saying isn't true, but I think you're catching a pattern. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is back to sine. And so the fourth derivative of sine of x is sine of x. Cycles back to itself, which is probably what you're saying. Okay, but now let's find the derivative with respect to x of the tangent of x. What is tangent?
1 over c.
Sine of x.
Sine over cosine. So this is a derivative with respect to x of sine of x over cosine of x, right? And how do you take the derivative of a quotient? Low d high minus high d low, square the bottom, away we go. So the bottom times the derivative of the top. So cosine of x times, what's the derivative of sine?
Cosine x.
Cosine. So the bottom times the derivative of the top, minus the top. What's the derivative of the bottom?
Negative sine.
Negative sine, so that's going to make this a plus and another sign, right? All over the bottom squared, which is cosine squared of x. Good? So rewriting that, that is equal to cosine squared of x plus sine squared of x all over cosine squared of x. What is cosine squared plus sine squared?
1.
1. Back to our Pythagorean identity. So it's 1 over cosine squared of x. What is 1 over cosine? That's secant. It's always the one you don't want to be. The c goes to the s and the s goes to c. So-
secant squared.
Cosecant, or secant squared. Yes.
So I need. Oh, okay, okay.
So, derivative of tangent, secant squared. All right, let's find the derivative now of, which one should we do next?
Secant x.
Cotangent is almost identical. It's cosine over sine, so probably not worth doing, but let's do secant, that one might be more interesting. All right, so derivative of secant. So derivative of secant of x, what is that equal to? What is secant?
I forgot your.
It's 1 over cosine, right?
You forgot your c.
Secant of x. All right. And that is 1 over cosine of x. Okay, how can we solve that thing?
Cosine is.
The derivative of that.
What is 1 over cosine?
How do we do the derivative of 1 over cosine?
The same
We could use the quotient rule. That's one way to do it. Let's do it using the quotient rule. So that's going to be equal to the bottom
Cosine.
times the derivative of the top. What's the derivative of 1?
0.
0. Minus the top times the derivative of the bottom,
Negative sign.
negative sign. So that's going to be plus sine, like that, right?
Why?
Negative sign turns
Oh,
the minus
negative.
into a plus. All over the bottom squared,
Cosine.
right? Now, simplifying, that's going to be equal to sine of x over
Squared.
cosine of x. I'm going to write it like this, times 1 over cosine of x, just to help you see it. See how that's the same? And sine over cosine is
Tangent.
tangent, and 1 over cosine is
Secant.
secant.
Oh, would you look at that?
Now, another way we could have done this one, let me do it a different way here. I could think about the derivative with respect to x. Secant of x is the same thing as the derivative with respect to x. Oh, we didn't do the chain rule. Never mind, we don't have chain rule yet. So, forget that. Okay, so, and then calculating the derivative of cosecant is basically identical to doing it for secant. Good? So let's do some quick examples and then we'll call it. So what's the derivative now of x squared minus sine of x? So what's the derivative of x squared?
2x.
2x.
2x minus
Cosine. Cosine x.
cosine x. Should probably get out of your way so you can see it.
Is that
Okay, so that's the derivative of that. Let's do the derivative of this one.
Same thing.
Bit trickier.
Is that a times or a minus?
That is a multiply sign. A dot.
Okay, so 2x.
That's gonna be our products rule.
It's your product rule. It's the first times the derivative of the second plus the second times the derivative of the first. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So it's 2x times sine of x. Putting the 2x first. You see it?
Okay.
Alright, let's try another one. What's the derivative of sine of x over x?
That's it.
That's it.
That's just one. Oh.
No, we're not saying the limit as x approaches 0 is the
That's
same.
0.
We're saying what's the derivative of it?
0.
No, not even close. So what is the derivative with respect to x of a quotient?
It's the x. Or it's sine.
It's the bottom
Oh.
times the derivative of the top.
Cosine.
Cosine of x.
Then what?
Then.
Plus sine of x.
Minus, right?
Yeah.
Oh, it's going to be a plus when it's all said and done. So the bottom times the derivative of the top minus the top times the derivative of the bottom.
Sine x. 0.
Because the derivative of the bottom is just
0. Constant.
1. What's the derivative of x? What is the derivative of x with respect to x?
What is 1?
1. What is the slope of x?
1.
1.
What happens if I take x to the 1, I bring the 1 down and make it a 0, so we get 1 times x to the 0, what do I get?
1.
1. 3 different ways you can think about that as being 1. Not 0.
1. So just sine of x.
So, minus the sine of x all over
Sine of x.
X squared.
X.
x squared, the bottom squared. Low d high minus high d low, square the bottom, away we go. Good?
Yeah.
Alright, we'll call this one the last one and call good. So, this one, let's find its derivative now.
Is that?
Cosine of x over 1 minus sine of x. So, what do I write first? You tell me what to write.
Cosine x. X.
What do we write first?
X.
X? Where are you getting an x? How do you take the derivative of a quotient?
Wouldn't it be cosine x?
Well, subtract sine x
The bottom
times negative sine x.
times the derivative of the top.
So
Then
you're saying
color-
that you subtract them when you're doing the quotient?
Yes.
Okay, so subtract
Cosine x.
The top negative cosine of x. What's the derivative of 1? 0. What's the derivative of sine? Cosine, make it negative. All over
x sine cosine x squared.
1 minus sine of x
Squared.
all squared.
Okay, alright, bottom squared.
Low d high minus high d low, square the bottom, away we go. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared.
Okay.
And then you can do the algebra, see if stuff cancels. Good? Alright,
We should do the algebra.
well, you can work it out. It's an example problem, I'm sure. These are all example problems from the book, so you can see them all to your heart's content. And you can come back and look at the recording and make sure it lines up. So, we'll call it there, running low on time. And we'll do chain rule next week.